Appreciate the opportunity to be here today to talk a little bit about the landfill industry and modern landfill technology as it may apply to the topic that we've been talking about today. The landfill industry has changed somewhat. And some of you may be well aware of that, but for those of you that aren't, I'm going to provide a little overview of some of the technology, how we can now, to some degree, control some of the degradation processes that are going on in the landfill and how that may apply to the management of these compounds. Increasingly, as we've heard today, I think one of the earlier speakers had a statistic up that about 54% of the disposal of pharmaceuticals particularly was in the trash, which ultimately ends up in the landfill. So increasingly we're becoming our facilities are becoming home to these various personal care products, pharmaceuticals, and other products that we don't have an end use for, we're not recycling. And I would say our projection is for that to increase as recycling rates continue to go up. So we're pulling a lot of material out of the landfill, and we're pulling even organics out of the landfill now. So what's increasingly going in is the stuff that we're really having a hard time, society's having a hard time finding other solutions for. For instance, this protocol that came out last year from the federal government, and I'm sure many of you are aware of this, really is the first directive of its kind directing people to dispose of pharmaceuticals, in this case, in the trash, in sealed containers to discourage reuse with kitty litter, other things like that. Obviously, this is going to increase the 54% perhaps to something higher, which is probably a good thing because, as I'll show later, a landfill environment is a inherently more stable environment, more long-term environment for these than some other environments. But I think, one of the earlier speakers had talked about community pharmaceutical take-back programs. I mean, that's something that I know when my family and I moved 2 years ago, we had children right at that age when they're about 8 and 12, when you'll give them just about any kind of prescription to keep them quiet. They're sick a lot when they're younger, and when we moved, we ended up with an unbelievable amount of these personal care products and pharmaceuticals that, and I think everyone ends up in that position at some point. It's what do you do with these? A little quick overview on modern landfill technology, what we're working on at Waste Management. This is just a drawing of a bioreactor landfill, or I prefer to call it a liquids addition landfill because a lot of people get terrified when you say bioreactor, but really all we're trying to do is expedite the degradation processes. And our two levers that we can pull on that are to add liquid. We can also add oxygen into the waste mass to really begin the composting process. And we've got a lot of sites where we've researched this, of course, in a much coarser fraction than coarser method than a lot of the talks were this morning, where we're measuring, temperature, we're measuring BOD/COD ratios and VOCs and things like that. We're really not looking for these compounds yet. As I mentioned, another thing that we've been working with, and we've got some full-scale systems in, is the addition of oxygen, mainly not to convert to an anaerobic process because we value the methane gas production as an alternate energy source, but really to speed up degradation, to get the temperature of the waste mass up. So we inject oxygen to get the temperature up, and then we convert to anaerobic so that we can access the gas and thereby compress the degradation time frame for waste in a landfill from where it might have been 30 to 50, 100 years, a decade or so ago, down to maybe 12 to 8 to 20. Distribution methods, how do we get these liquids in? This is just one example where we're using distribution lines bedded in tire chips to introduce the liquids in. Liquid distribution is a challenge for us because waste is such a heterogeneous medium. Biosolids, landfill industry, I think I saw a statistic where about 2 million tons of biosolids end up in landfills every year, and there's been a lot of discussion that those can be enriched in some of these compounds. We particularly like biosolids because they they expedite, and we can get higher methane generation rates out of those, which we can then convert into electricity. So as a result of these new processes in the landfill, how have conditions changed? One of the things obviously is temperature that we keep an eye on, and with aeration you can see we're able to get the waste temperatures up very quickly up to 80 degrees C. Typical landfill temperatures are more on the range of 20 to 40 degrees C, but we're able to control this a lot more than we were just a decade ago. And I have a series of slides here just to kind of show you the type of data we collect in these as we're experimenting with different technologies to expedite degradation in a landfill. And in this particular example, I've got a control cell, which would be engineered containment, no liquids added, as compared to a cell where we're adding liquids, accelerating degradation. And the control cell is represented by the dark blue diamonds, and the recirculation or liquids addition is the maroon. In this case, you're seeing the gas production in the same exact volume of waste, how much addition, this is cumulative gas production that we get if we add these liquids. BOD-COD ratios, again, looking where we're what you may call dry tumbing it. You put the waste in a giant Tupperware container. You don't add liquids. The COD-BOD ratios stay low. The waste has such an enormous absorptive capacity that it's just not getting enough liquid to degrade. It comes in at around 20% moisture content by weight. Optimal would be a good 10% above that. We need almost 80 gallons for every cubic yard just to really get into a good degradation of the material. So when we add liquid, obviously we mobilize the BOD-COD and then start the degradation process. This is a closed loop recirculation where all the liquid that comes through the waste mass goes through the top. So you're seeing that degrade relatively quickly. Volatiles, we track volatile organic compounds. There's probably the primary regulatory concern for impact to the environment that we track. And you can see the chlorinated compounds decrease rather rapidly when we add liquid. In the dry tomb, the old landfill technology where we wouldn't add liquid, none of these really get mobilized because there's very little liquid there. And they're there, perhaps you could argue that they're there in the event that you had liquid go in 10, 20 years in the future, you could mobilize them. So that we would rather do that now rather than later. But you can see these organics through liquids addition, and this is roughly about an 8-year period, go down to very low concentrations, not low by the standards we're talking today, but singular part per billion levels. Metals, some metals follow this curve too, again, where we're adding liquids, we're increasing degradation, we get an initial spike. These are milligrams per liter. In this case, manganese, iron looks very similar. Arsenic behaves a lot more erratically in a landfill environment. But we get back below the dry tumor control cell concentrations within a few years. What does the material look like? I mean, this would be material of roughly the same age, same source material, and these are the wells that we drill. They're 3-foot diameter wells that we use to extract gas for power generation. And believe me, this smells really bad. I mean, this is undegraded waste, same age, and then this is where we've added liquid. So this would be that blue diamond lines would be represented by this part of the facility, and then the maroon squares by this one. This has no odor. It's like if you went to Home Depot and bought a bag of compost and opened it up. So we're kind of excited by that, and listening to some of the talks today, it should be a good medium to attenuate or absorb some of these compounds. But we really don't know. We don't know a lot about it at this point. Findings, we can move out of the acid phase. Landfill goes through distinct phases in degradation. We can move through those phases very fast and get into methanogenesis. So we've got anaerobic conditions, we've got sulfate reducing conditions and methanogenesis going on in the landfill. We can get the temperature up, and we can somewhat control that now, and increase the liquid residence time. And this is an area where there's a lot of research occurring right now, is just trying to figure out how long. For instance, one of our facilities, we added a 9-acre area. We added about 18 million gallons of liquid into that area for a decade. And it took 9 years before the flows at the bottom of the waste mass, it was about 100 feet thick, changed before they increased. So we've got, even in that situation, probably 10 years to 50-year residence times for liquids in these modern landfills, because modern landfills are so much larger and the waste is so much thicker that you just have a longer and longer residence time. There's about 1,600 landfills presently in the U.S., whereas 10 years ago there was over 3,000. So the trend is for fewer but massive facilities, which change a lot of these parameters as well. And then we're able to manage our liquids on site and not be as reliant on the wastewater treatment plants as well, if we can add the liquids back in. Landfill fate, I think these are pretty obvious. As I mentioned, we really don't know a lot about this. I think there's been a lot more research done in Denmark and in Germany. I know I've read some papers that look very promising that the Germans have done on their landfills and the fate of some of these products in those facilities. And we are currently putting together a white paper on that, trying to figure out what research exists out there. If these compounds are leached from the waste mass, obviously most of our facilities now have closed loop recirculation, so they would have another opportunity for adsorption or attenuation. Some we have on-site treatment. A few facilities in Illinois have that, and quite a few of them do still rely on wastewater treatment plants as well. And then, of course, we're collecting gas, so there is a potential for them to volatilize and be introduced into the gas. In my opinion, that's probably not as big of a concern, simply because we're collecting that gas and we're burning it in turbines.
Have you done any measurement of leachate from your pharmaceuticals?
We have not measured specifically for that. We measure for a broad list, a lot of the pesticides and herbicides and things like that. Surprisingly, I did a study for actually for Illinois when we were changing the regulations, and like about 99% of the organic mass in our leachate is VOCs and phenols, and very few pesticides and herbicides. Now that could be they're degrading as they move through the waste mass. Perhaps they're not in there initially. So data needs. I think leachate characterization, your question exactly, is something that would be fairly simple to do. I know the analytical costs are quite high, but we have a system here where we can collect a sample what comes right out the bottom of one of these facilities, and we do that routinely. And then obviously looking at the fate of these products and compounds in the landfill environment, and maybe there's things we can do to improve those conditions for degradation. And then policy development and disposal guidelines. I like to see what has come down from the federal government. I mean, at least it's giving people some guidelines. And I know there was someone that talked earlier about some collection activities that are occurring, and that's great. But I don't think there's a lot of information out there for people to know what to do with these things, like there is for recycling, and they've kind of sort of been ignored. So I think we need more education. That's all.